Welcome back for another in-depth topic on game development. In this video, we're going to talk about steering behaviors, which is a simple way to add realistic and complex seeming movement to the computer-controlled sprites in your game. For this first video, we're going to be looking at the seek behavior, which is how you make a sprite chase a target. There are lots of other steering behaviors, which we'll cover in later videos. For reference, if you want to learn more about steering behaviors, a really great resource is this website for the book called The Nature of Code by Daniel Schiffman, especially Chapter 6. Chapter 6 is all about all sorts of steering behaviors and ways you can get sprites to do intelligent-looking things like following lines, following the leader, avoiding obstacles, all that kind of thing. And, for example, here's some examples of line following, where the sprites will try and stay on a line and follow that. Okay, to start out, I've just made a little program here that's going to spawn a mob sprite. And this mob sprite is going to have 3 vectors associated with it. A position vector, that represents where the sprite is located on the screen, and it's going to pick a random X and a random Y when it spawns. So it's going to spawn somewhere randomly on the screen. And then it's going to have a velocity vector, and that represents how much the sprite will move every frame, how many pixels it will move, and in what direction. And I'm going to make that equal to the max speed, which I set to 5. So 5 will be its maximum speed. And I'm just making a vector with that pointing to the right. But then I'm rotating it, I'm applying the rotation to it of a random number between 0 and 360. So it'll point in a random direction. So it'll be turned differently each time we spawn it. And then it's going to have an acceleration vector. And the acceleration vector represents how much the velocity is changing each frame. And that's going to be set to a 0 vector, so it's not going to change. So its velocity will be steady. So when we spawn this sprite, it'll spawn randomly on the screen somewhere, moving in a random direction. And every frame, it's just going to update by, we take our velocity and we add the acceleration, right? Because the acceleration is how much the velocity changes. If, and I have this little if here, just to make sure that our velocity never gets bigger than our maximum speed. So we check the length of the velocity vector, and if that's greater than 5, then we're going to scale the length of the vector to be 5. And that way we won't ever go faster than 5. And then we take the position and we add the velocity to it, and now we have our new position. And then I have some ifs here, just making the sprite wrap around the screen. Okay, so when we run it, we get a random sprite on the screen going in a random direction. And if I hit the V key, I've turned on, I've added a little thing to show the vectors here. So this green line is the sprite's velocity vector. And you can see it's supposed to be 5. I'm drawing it bigger just so that you can see it on the screen, because 5 pixels would be kind of short. But you can see that the velocity vector is pointing in the direction it's going, and the sprite has no acceleration, so its velocity is never changing. Always stays the same. Now let's say we wanted to have the mob chase the mouse around the screen. So I always want the mob to try and move towards the mouse. So I can make a little method here called follow mouse. And what I'm going to do is find out what the position of the mouse is. We get the mouse's position, right? And that's going to be an XY pair, which we can think of as a vector representing the mouse's position, and we already have a vector representing the mob's position. So how do we find the vector that points from the mob to the mouse? Well, let's look at some vector math for a second. Okay, so let's say I have 2 vectors, v1 and v2, and these are the values of them. Well, adding 2 vectors together means you just add their x's and you add their y's. So v1 plus v2 is 50 plus 10, which is 60, and 30 plus 20, which is 50. And another way to look at that is if you add two vectors, it's like putting the second one on the tip of the first one, and you get the vector that points all the way to the end. Right? So that's this vector is 60, 50, this blue vector. And subtraction is works pretty much the same way. If you take v1 minus v2, that's the same as adding v1 plus the negative of v2. Just like when you use numbers, subtracting a number is the same as adding a negative number. So negative v2 is just v2 pointing in the opposite direction, right? It's going to be negative 10, negative 20. And that's what this little vector here is. So if we add those together, we get this vector, which is 50 minus 10 and 30 minus 20. Well, another way of looking at that is if v2 and v1 both represent positions for where an object is, right? This is where the mouse is, v1, and v2 is where the mob is. Then this vector is pointing from v2 to v1. So if you take v1 and subtract v2, you get a vector pointing from v2 to v1. If we did it the other way around, if we said v2 minus v1, we would get the same vector but pointing in the opposite direction. We would get the vector from v1 to v2. Okay, so when you subtract two vectors, you get the vector pointing from the second to the first. And that's all we're going to do to get the vector pointing at the mouse. And we want that to be our acceleration because we want to accelerate towards the mouse. So we're going to take the mouse position and we're going to subtract the mob's position. And now we have a vector. Now we have the vector pointing from the mob to the mouse. But the mouse might be far away, or it might be nearby. We don't want to accelerate ridiculously fast when the mouse is on the opposite side of the screen. I want to always accelerate at a steady speed. So that means I want to take this vector that I just got and I want to normalize it. And all normalize means when you're talking about vectors is you're making the length 1. So this takes the vector, it keeps pointing in the same direction, the length just becomes 1 instead of whatever the length was before. And this is also called a unit vector. And unit vectors are super useful because they help you figure out directions, right? They tell you what direction something's going in, but they don't worry about the distance or the length or the speed or any of those things, right? They just worry about the direction. And if we have the direction of something, we can always scale that vector to whatever size we want. So let's multiply that by 0.5. So now our acceleration is going to be 0.5 in whatever direction the mouse is. So in our update, we will just now use that follow mouse. So we follow the mouse. And now what you'll see is that the mob is going to accelerate towards the mouse. If I turn the vectors back on, you'll see that the velocity is changing to go towards the mouse. And that's pretty good, but I'll turn the vector back off here. It's not quite natural, right? The mob kind of turns on a dime, and it looks kind of robotic and artificial. And so we can do better. We can make this look much more realistic and smooth. And that's what the purpose of these videos is talk about steering behaviors. And steering refers to ways to make your movement look natural. And there are all sorts of steering behaviors that we'll be talking about in later videos, but in this one we want to talk about the seek behavior. And we're just going to give it a target. So this function will calculate what the seek vector will be towards some target. So what do we mean by seek behavior? Well, let's look at another diagram. Okay, so here we have our mob, and this blue vector represents its current velocity. It's currently traveling in this direction. And then here's our target over here, the mouse pointer. So this red vector represents our desired velocity. Right? The mob wants to go towards the target. So it wants its velocity to be this. And the length of this will be the max speed, right, which we set to 5, right? So this is what it wants. This is what it currently is. If we instantly just set its speed to the desired, then it would look really artificial. So what we want is we want some steering. And this is the steering vector. So if we just take the desired minus the velocity, we get the vector pointing from velocity to desired, right? And so this is the steering force. This is the direction or the force we want to apply to move our velocity to the desired. Now, if we used it at the full length, then it would instantly change from velocity to desired. So we're going to scale this. And how much we scale this depends on what type of object our mob is. Is it a cheetah that can turn really fast? So the steering force should be large. Or is it a slow lumbering elephant, in which case it should be really short and should take it a while to pull its velocity over to the desired. So we can control that by how long we make our steering force vector. Okay, so now we can go over here to our seek and set it up. So we want to set what our desired is. Now we don't really need this to be a class variable, self.desired, but I'm doing that so that I can draw it. And you'll see later I'm going to have it draw its vector. So the desired is going to be target minus pos dot normalize times the max speed, right? So that gets us that desired vector. The vector pointing from the mob to the target, and its length will be max speed. That's the direction we want to go. And then our steering, I'm just going to call it steer, is just desired minus velocity, right? Just like we saw in the diagram. Now we need to just scale it to the right length. So I'm going to make a variable here called steer. Let's call it the seek force. And that's going to be the maximum number that it could be. Let's set that to 0.1. So if the length of our steer vector is greater than the steer force, or sorry, the seek force, then we take the steer and we scale it to the length of the seek force. Okay, and then we return steer. So now our seek force will give us back, our seek method will give us back whatever the steer force should be. Okay, and so now on our update, we're going to get rid of following the mouse. We're not going to follow the mouse anymore. We're going to do our acceleration. So what we want to do is we just want to say our acceleration is equal to seek, self.seek, and then the target is going to be get pos for the mouse, right? So we're seeking towards the mouse. And then I want to draw the, I'm going to add to my draw function down here, where I draw my vectors. I'm just going to add, and I'm just going to copy and paste this real quick, just so that we can see what the desired is as well. So we're going to see the current velocity and the desired velocity. Okay, so let's see what that seek behavior looks like. Okay, So there is my mouse, or my sprite. See, it's following the mouse. That's good. If I turn on the vectors, you can see how the desired is always pointing towards the mouse, and it's always the same length. It's always the max speed. But it takes a little bit of time for that velocity vector to move around and be equal to the desired. And so this is with our seek force set to 0.1. Right? So you can see, if you wanted to see what a slower thing would be, let's make it half of that. Let's say it was only 0.5. Then you'll be able to see that it takes a lot longer for the sprite to change its velocity and get it all the way around to there. Right? So this is a big object with, a lot of mass or something. It doesn't turn on a dime. And if our seek force was a lot higher, then you're going to see it can change really fast. Now, one other thing you've got to take into account when you're doing the seek behavior is that when you, what do you do when the sprite reaches the target, right? See, right now, what happens is we get this wobbling effect. And if we turn on this, you'll see why. It's because desired is always set to the maximum speed. So as soon as we get past the target, we want to go full speed in the other direction. And then as soon as we get past it, we want to go full speed in the other direction. So there's no way to actually stop when you reach your target. Now, if this is an enemy that's chasing you and is going to hit you when it runs into you, that doesn't really matter. But sometimes you want the sprite to reach the target and stop there. So what you want to do to adjust this is you want to use something called an approach strategy. And so what the approach strategy is that when as you get closer to the target, you slow down. So let's just copy this. I'm going to duplicate this, and I'm going to call this seek with approach. Okay, and this is just going to let us know, or this is going to check to see if we've gotten close to the target, and if we are, then we're going to slow down. Now, you could do this in a couple of ways. The most flexible way is to basically define a radius around the target. And if you're outside of that radius, you run full speed towards the target. But as soon as you cross that line and get close enough to the target, you start slowing down. And so we'll set an approach radius. Let's capitalize this. And that's how far away we're going to look to slow down. Okay, and I'm going to set that to 150. Okay, and so now what we want to do is we want to figure out how far away we are. Okay, so before we normalize this, this is going to tell us the distance from the target to the position, right? Or the vector from the target, from the position to the target. And so the distance is just going to be the length of that. Okay, and then we can normalize the desired. And there's a handy version of normalize. It's called normalize in place. And we don't necessarily want it to always be max speed, so we're going to get rid of that. So normalize in place just says take this vector and normalize it, but keep the variable name the same, right? We don't have to set it equal to anything. It just normalizes it as it is. Okay, so now we know what our desired direction is going to be. We need to figure out what our speed should be depending on where we are. So if our distance is less than the approach radius, then we need to take our desired and we need to multiply it by some fraction of the max speed. So if we take our distance and we divide by the approach radius, then we know how close we are to the center, right? If we're halfway from the edge of the circle to the mob, then we're halfway there, right? And so we should go at half speed. So we're going to multiply that by max speed. Okay. Otherwise, we're going to go max speed. Okay. So if we're outside the circle, we're going to go max speed. If we're inside the circle, then the closer we get, the slower we go. Okay. So now our steer is the same. The stuff stays the same. Our steer force is still going to be the same. We're still trying to pull over towards our new desired vector. And so let's just change this to using seek with approach. And what I'll also do is, just so that we can see the circle, I'm going to add to the drawing here that we're going to draw a circle at the mouse position so that we can see it. Okay, so there's my sprite acting just the same way as it was before. Actually, let me go back over here. I'm going to put this back to the 0.1 because that was a good medium value. Okay, so there's our mob behaving as it was before. But when it gets close, it slows down and stops at the target. And if I turn on the vectors, you can see there's my approach radius circle. And as soon as I get inside it, my desired vector gets smaller. So the steering force pulls it towards that smaller value, not towards the maximum. And depending on what you set your approach radius to, you can have the object stop quickly or take a little time. And that is another thing you can adjust to make this behavior look all sorts of different ways, right? You can adjust that depending on how you want your mob to behave. So that's the seek behavior. In future videos, we'll talk about all sorts of other steering behaviors that you can implement to get a lot of different effects into how your mobs and other computer-controlled agents on the screen behave. One example I'll give you before that you can try on your own is the flee behavior is basically the opposite of seek. So you would just reverse this, right? Your desired is going to be the opposite direction, it's always pointing away from the target, and then you'll always flee. Experiment with that. You might want to do some kind of distance, so you only flee when the target gets too close to you. But I'll let you experiment with that on your own, see if you can get that to work, and we'll talk about that in a later video. Okay, thanks for watching, and hopefully this was helpful to you. I'd appreciate it if you could like the video, subscribe if you're not already, and I will see you in the next in-depth video.